Okay, so we are trying to work towards understanding this beautiful fractal structures. And to do that, we have to understand iterative functions. And to understand it properly, we need a notion of limit using complex numbers. So this is what this video is about. We'll run through definitions and some tools for evaluating limits. Okay, so we're going to run through a lot of it here. Just so you know, we're not going to do too much on knowing the precise definition and proving all the tools. You do that in a real analysis class. Here, I want you to understand the definition and be able to apply the tools. So let's go through this. Okay. So let's say we have a sequence of complex numbers. What happens to this sequence? So here's an example of a sequence in complex numbers. I, -1/2, -I/3, 1/4, I/5, and so on. So this sequence is generated by nth power of I divided by n. Right. So if you kind of plot what we have so far, I starts out here. -1/2 is somewhere here. -I/3, 1/4, and so on. So if you look at the plot, it's reasonable to say that this thing is kind of spiraling towards the origin. So we want to be able to say this sequence converges to 0. And how do we have a mathematical definition that says that? So informally, a sequence converges to a limit L. So you have a sequence and it converges to some limit. Let's say L is some kind of complex number. If the sequence eventually lies in any small disk centered at L. So if we want to say our limit is the origin, we want to be able to draw any small disk. So imagine like a radius of 1/1,000,000 or something. And no matter how small I choose that disk, eventually the sequence is trapped within that disk. It doesn't have to be inside it initially. It could jump in and even jump out. But after some point, there's a point of no return where it's trapped within that disk. So that's the informal definition. Let's look at the precise definition. Okay. So we have a sequence Sn of complex numbers converges to L if for all epsilon greater than 0. So choose a positive number, and there exists this n. N is the point of no return, such that the modulus between the nth number in the sequence minus L, the limit, is within epsilon, right? So this looks like absolute value, but it's modulus, right? This could be a complex number. And you're within epsilon after a certain point, after the point of no return. So capital N, if you look at any n larger than that, it'll never leave that disk. It's always within epsilon of L. And when this condition is satisfied, this is how we write that statement. So limit as n goes to infinity of the sequence Sn is equal to L. Okay. So let's apply it into this initial sequence that we had. So we want to be able to say limit of I to the n over n as n goes to infinity is equal to 0. All right. So pick any epsilon greater than 0. So pick any positive radius. And we want to show that this thing is within epsilon for large enough n. Okay, so how do we do that? Well, we choose the point of no return to be some natural number n that's greater than 1 over epsilon. So if epsilon is small, 1 over epsilon is very, very large, then what do we get, right? Well, this expression is same thing as subtracting 0 doesn't do anything. So it's the modulus of I to the n over n. We can look at this fraction as the modulus of I to the n, but modulus of I to the n is always equal to 1 because I to the n is rotating between I, -1, -I, and 1. Okay, and denominator is n, modulus of n is n, so I just write n. If we have n is greater than or equal to n, then 1 over n is less than or equal to 1 over capital N. And if you look at this condition, if capital N is greater than 1 over epsilon, just bring the epsilon to the left-hand side by multiplying by epsilon and dividing by capital N. Then we can get that 1 over n is less than epsilon. Now, if you're wondering, how did I get this condition to work out in a computation? What mathematicians do is they first do the computation, whatever you want it to be true. So you get this expression 1 over n, and you want that to be less than epsilon. So you work backwards. From there, you can rewrite that. Well, that means that n had to be greater than 1 over epsilon. So you kind of work backwards, and when you read the proof from front to end, it looks like, where did that come from? But that's how they found it. Okay, so the limit of that expression is indeed 0. Let's see. Let me go to the next page here. Okay. So here are some facts that are good to know, right? If you have 1 over n to any positive power p, so p is a positive real number, then denominator is going to get bigger and bigger. So eventually, it's going to get close to 0, right? You could do a similar type of argument where capital N is chosen greater than epsilon to the 1 over pth power. So try to work that proof out. In fact, multiplying by a constant doesn't change the limit when the limit is equal to 0. So any constant divided by n to any positive power p is going to go to 0. So this is going to be a fact that we're going to use frequently. Another thing that we can work out is that if the sequence is nth power of a complex number q, sorry, positive or non-negative number q, I guess it works with 0 as well, then when you take higher and higher powers, it's going to get smaller and smaller. So this goes to 0. And because we know that for real numbers, if the modulus is less than 1, it does the same thing, right? Because when you raise complex number to the nth power, the modulus behaves like real number. Okay. And also another good thing to know is that if you take any real number, positive real number, and take the nth power, so if you take the nth root of large number, then it gets smaller and smaller. If you take nth root of very tiny number, it gets bigger and bigger. And they all approach 1. Right? So the nth root of any positive number approaches 1. Okay. Some other limits, rules for limits that are, I think, intuitive, but you need to check that these things still work out for complex numbers, right? So convergent sequence are bounded. So if something is convergent, then after finitely many points, it gets trapped within that disk of radius epsilon. So it's bounded, right? Because the disk is bounded, and there's only finitely many points outside. So there's the maximum distance away from that disk. Okay. If you have two sequences that converge to limits L and M, then the limit of the two sequences added together is going to be the sum of the limits. You could say the same thing about multiplication and division as well. Of course, provided the denominator is not approaching 0, then some weird things could happen. Okay, so I hope those are not surprise. There's a very easy way to compute the limit if you have an expression that looks like polynomial divided by polynomial. So some rational expression of complex numbers. So what you do is when you look at a rational expression, you look at the highest power of n in the denominator and divide everything by that. So what I mean by that is on this first example, we have n on the denominator. So we divide top and bottom of the fraction by n. Then what we get is n over n is 1 in the numerator. In the denominator, we get 1 plus 1 over n. Of course, 1 over n constant divided by n goes to 0. So we just end up with 1 over 1 or limit of 1. You could do this with quadratic expression as well. So in the denominator, n squared is the largest power. So I divide top and bottom by n squared. This is what we get. And then we just look at what they converge to. So everything to any positive power over n is going to approach 0. So what we're left with is 3 divided by I. If you multiply top and bottom by I, you'll get that this is actually equivalent to negative 3i. Okay. This thing works even if the powers on the top and bottom do not match. So if here, if you divide top and bottom by n, we get that denominator approaches 1, but the numerator explodes to infinity. So large number divided by 1 is going to be not bounded. So no limit here. It's approaching infinity. Okay. And what would happen if the denominator has higher power? So in this example, we get 0 in the numerator, and on the denominator, we just get I. So 0 divided by I is 0. And that's going to be the limit. And so this is a handy trick to get expressions like this. Okay. Some facts. Sequence of complex number converges to 0 if and only if the sequence of the modulus converges to 0. So sometimes computing limits of real numbers is easier. So you can kind of reduce the dimension, right? Like, because when you're working with complex numbers, there's the real and imaginary part. You have to kind of handle them simultaneously. But if you look at the modulus, then it's just one real number. So you can compute how that approaches to 0. Something a lot of times this will give you a way to compute it quickly. Even if you can't do this, maybe it's not approaching 0. It is possible to handle limits using just real limits. So if you want to show that xn plus iyn converges to some x plus iy, then you can look at the real parts and imaginary parts separately and prove the limits that way. So you could look at it one at a time. Okay, and some couple of the theorems that's useful. Squeeze theorem. So this you can only apply for real numbers, but maybe using it on modulus will help as well. So if you have sequence of 3 sequences, and maybe the smallest sequence Rn and the largest sequence Tn is easy to compute the limit of. So let's say the limit of the smaller one and the limit of the larger one, they all converge to the same limit L. Then the sequence in the middle, no matter how complicated they look, you would have the same limit. So sometimes if you have a complicated sequence, then you could maybe sometimes overestimate that sequence and underestimate that sequence. With a simpler expressions, maybe you can take the limit. And as long as the limit is still the same, the original sequence has the same limit. Another useful theorem, monotone convergence theorem. So if you have a bounded sequence, so if it's bounded and monotone. So when I say monotone, I mean function it's not, it's always increasing or always decreasing, right? It only changes in one direction. If it's monotone and bounded, then it has to converge. Right? If the sequence is increasing and it never crosses that line, then there's no way to go. It has to stop at some point. Okay. All right, so that's the complex limit of sequences. We also need a notion of limits for complex functions, and not taking the limit of n goes to infinity, but also taking the limit as z gets closer and closer to a particular complex number. So that's what I wanna talk about next. So informally, f of z has a limit L as z approaches some particular complex number z naught. If f of z gets close to L as z approaches z naught, so let's write that down. So this is the formal definition. Again, we're gonna use a disk and eventually gets trapped in the disk type of idea. So for any positive radius epsilon, there's some delta. So delta is going to be the radius, how close you are to the z naught. So as long as you're close enough to z naught, then the output value is close enough to L. That's what you want to say. So if epsilon is greater than 0, there is some radius delta such that whenever z is close enough to z naught, but not exactly at z naught, because maybe the function isn't even defined there, but close but not exactly at z naught, then the output value f is close to L. It's within disk of radius epsilon. Okay, so let's look at a computation of something like this. So let's say we have a function, some rational function f, z squared minus 1 divided by z minus 1. And let's say we want to take the limit as z approaches 1. We can't just plug it in because if you plug in 1, you get 0 divided by 0, which is undefined. But if it's some number close to 1, but not exactly at 1, then we can do some algebra to make it look simpler. So the numerator could be rewritten as z plus 1 times z minus 1. Just factor it out. Then z minus 1 cancels from the top and bottom. And this original expression is the same as z plus 1 as long as z isn't exactly equal to 1, right? But it's when you write it this way, the limit is obvious. As z gets close to 1, you can just plug it in. This is approaching 2. Okay, so that's a typical computation like that. Let's look at the argument function. So remember, the argument function is the function that gives you the angle that z makes with the positive real axis. And when I use capital A in the front, that means I'm looking at angle between negative pi and pi. Okay. So this is what we look like. So as z approaches I, if you get close to that number, the angle is also approaching pi over 2, right? It's approaching 90 degrees. So the limit is pi over 2. Again, if we're getting closer and closer to 1, the angle also gets closer and closer to 0. Okay, so that's the limit. The only weird thing that happens with this function is that because of how we cut the angle, if we're looking at negative 1, this guy does not have a limit because if you go slightly above the real axis, then angle is getting closer and closer to pi, right? The angle over here is close to pi, but if you go below the real axis, the angle is getting closer and closer to negative pi because this negative real axis is the cutoff point. The angle is approaching pi and negative pi from different sides. It does not have a single limit, right? So the limit does not exist. Okay. All right. Some facts that I hope is not surprising. So again, if f function has a limit at z naught, then f is bounded close to z naught. Okay. If the function f and g both have a limit, then the limit of the sum of the functions is the sum of the limits. You can say the same thing about multiplication and division, as long as the denominator is not equal to 0. So similar rules hold for function as it did for sequences. Okay. It's also good to know the definition of continuous function. So let's define that now that we know the definition for limit. We say the function f is continuous at a particular point z naught if the limit of the function at z naught agrees with the actual function f. Okay, so when I write that down, I'm actually saying 3 different things. Is that function is defined at z naught. So although it's actually possible to define a limit without function being defined at z naught, for it to be continuous, it has to be defined there. You also have to converge as a limit. And also, the limit and the value of the function has to agree. So it's really, you have to check those 3 things. Okay. Some examples of continuous functions. Constant function is of course continuous. Function z is continuous, right? Like as z approaches z naught, it approaches z naught, so it works. Polynomials work because all this multiplication and addition rules hold. automatically, if those two things are continuous, then polynomials will also be continuous. Other things, modulus function is continuous, so that's good to know. And in fact, even rational functions, so fractions of polynomials, are continuous as long as you stay away from division by 0. So then the function will not be defined. So it can't be continuous there. Okay, I think that's how much I want to cover for this video. So I will see you in the next video.